Our goal for today is to have a little bit more discussion about convergence, and we're going to phrase it in terms of what we call ordinary points. But really our big goal is more practice. So we're going to do more practice in working with the series solutions, and that means recurrence relationships, finding our first few terms, and so forth. So we start with the idea of ordinary points. Now you should basically think of ordinary points as nice. So suppose you have a differential equation, y double prime plus p of x y prime plus q of x y equals 0. So this is our second order, it's linear, and we say, all right, a point is ordinary if these functions are analytic. Now that's a very technical sounding term. It basically means they're nice functions. You can take lots of derivatives. Now, it's not so important about ordinary points. What's important are the non-ordinary points, which are called singular. So those are not nice, and that's where things start to break down. And so what's true? Well, what's true is if we're at an ordinary point, then our series solution works nearby. How near? You say you keep going until you hit your singular point. What if there is no singular point? Then it goes all the way. So this gives us a really quick way to find radius of convergence. Namely, we say, all right, look at these functions. Where do they break down? And in particular, if they're rational functions, which means polynomial over polynomial, you say, all right, where do I divide by 0? And there you go. That's it. All right, well, let's do some practice, and let's see what happens. So, we're asked to determine whether 0 is an ordinary point for the following differential equations. All right, well, we have xy double prime plus sine of xy prime plus x squared y equals 0. What do? Well, we want to get our coefficient in front of y double prime to be 1. So we say, all right, so let's call this A. So for A, we would say this is y double prime plus sine of x over x y prime plus x y equals 0. Now the question, are these functions attached to y prime and to y, are these nice? Well, x, beautiful. We love polynomials. Mwah! What about sine x over x? Now, of course, sine x over x sounds scary because we have an over x, but if you think about sine of x, we actually have a nice series that converges everywhere. Sine x over x, you can divide everything in the series by x. You still converge everywhere. So what we have is that these are both analytic everywhere. Okay, well, what does that tell us? It tells us that yes, so we do know that 0 is an ordinary point. All right, great. Can we actually say more? And the answer is yes, we can. We can say that the radius of convergence would be infinity. Why? Because there is no singular point, so we get to go all the way out. All right, so that's A. Well, let's try another one, B. Okay, so what can we say about B? Well, y double prime plus xy prime plus square root of xy equals 0. Now we do the same things. Look at, since we already have the 1 in front of y double prime, look at what's in front of the y prime and the y. And we say, all right, x, beautiful. Square root of x, that's not beautiful. The problem is, what's true about square root of x? Well, at x equals 0, it's only defined for positive x, and moreover, it's coming in pretty steep. So this is not analytic at 0. So what does that tell us? Well, it tells us, forget it. 0 is not ordinary. So 0 is not ordinary, so we could say singular. Bad. It's not an ordinary point. So we wouldn't even try to find a series solution here at this time. Hopeless. Our tools don't apply. All right. Now that's 2 down, right? 1 to go. All right. So again, we want 1 in front of our y double prime. So we say, okay, y double prime plus x over x squared plus 2x plus 2 y prime plus x squared over x squared plus 2x plus 2y equals 0. Now, what's happening? Well, as we look, we say, hey, these are nice functions at 0, right? Because we're not dividing by 0. So we're like, good. So as long as you have a polynomial over a polynomial, as long as you're not dividing by 0, you're a wonderful function. So we know 0 is an ordinary point. Okay, great. Now, can we go further since we have space? Maybe we can. How far can we go? In other words, if we find the series solution, what's the radius of convergence? All right, so let's think about this. Well, our problem is, where do our coefficients break down? They break down where the denominator is 0. So where does x squared plus 2x plus 2 equal 0? All right, well, we can solve, right? We can do quadratic formula. Negative b plus minus square root b squared minus 4ac all over 2a. And if you clean this up, that's negative 1. Now, here you'll get square root of a negative 4, which is 2i divided by 2. So negative 1 plus minus I. Now, what does that mean? Well, it means that if you mark points in the complex plane, well, you have negative 1 plus I, negative 1 minus I. So those are our 2 points. Now, we're starting at 0. So what we do is we say, all right, from 0, how far are these points? Because those are the nearest singular points. So we're going to be fine everywhere inside of this circle. All right, so how far from 0 to negative 1 plus I? It's the same as 0 to negative 1 minus I. Well, you can think of it as there's a triangle. There's 1 in the real direction, 1 in the imaginary direction. Pythagorean theorem, 1 squared plus 1 squared equals that squared. So our radius of convergence will be square root 2. So, in other words, once we found the series solution, it wouldn't converge for all x. It would only converge up to a distance of root 2. Notice how easy this is. We didn't have to figure out the coefficients. We didn't have to say, okay, what's the ratio of the coefficients? It was just like, where do things break down? And however far it is to the breakdown, that's our radius. That makes things so much nicer. Isn't it great? I like it when things are nice. Let's look at this example. We're asked to use series to solve the differential equation. X squared minus 1 y double prime minus 6xy prime plus 12y equals 0. Notice we're not asked to like approximate a solution. We're going to find the whole thing. Okay, all right. So we're going to explicitly state the recurrence relation, give the first few non-zero terms for the 2 different sets of initial values. And our initial values are 0, 1, and 1, 0. And then we're going to compare the radius of convergence with that given by the fact. Okay. All right. So, what can we say? Well, We just have to do it, right? Now, if you saw this differential equation, you'd be like, ah! And let's hope that something nice happens, because it's not so obvious that we're going to get a nice answer. So let's just go for it. And how do we do it? Well, we'll follow what it says. Explicitly state the recurrence relation. So we're starting this by saying, well, let's think of y as a series. So sum 0 to infinity of c k x to the k. And now we're going to plug this into our differential equation. Well, actually, we're almost going to do that. We're going to make one little tweak. And our tweak here is to multiply through. So we're going to think of this as x squared y double prime minus y double prime minus 6xy prime plus 12y equals 0. All right. Well, what do we have? And so we plug in term by term. And what we're going to have is a lot of stuff. And so just be patient, work the process. So x squared. Now, y double prime. So let's go ahead and just write that out. That's the sum. K equals 0 to infinity. C sub k. First order will bring down a k. The next one will bring down a k minus 1. And we'll have x to the k minus 2. Okay, so x squared, y double prime, minus y double prime. All right, sum k equals 0 to infinity. C, k, it's the same thing, so we can just look over here and copy, right? Yeah, of course we can. No problems. It's all right to do that. Next up, minus 6x y prime. All right, so that's c, k, I forgot my sum. Sum k equals 0 to infinity. Can't forget that. It's important to put the sum in there. C, k, k, x, k minus 1. Plus 12y. So plus 12, sum k equals 0 to infinity of c, k, x to the k. All of that equals 0. Whew. All right. It's good that we have big paper, right? Big paper for big ideas. All right. Now, what do we have? Well, let's bring our terms inside. So what does that mean? Well, we're going to take our x squared and we'll bring it in. We'll bring our x and we'll bring it in. We can even bring in the 6, but that really won't matter right now. And you'll notice nice things are happening. X squared, x to the k minus 2, that'll be x to the k. X to the k minus 1, that'll be x to the k. And there's x to the k. Nice! So this is going to make things work really, really pretty. Okay, so catching up. We have sum k equals 0 to infinity, ck, k, k minus 1, x to the k, minus the sum k equals 0 to infinity, ck, k, k minus 1, x to the k minus 2. Now we have then minus 6, sum k equals 0 to infinity of ck, k, x to the k. And then plus 12, sum k equals 0 to infinity, ck, x to the k, and all that equals 0. All right. So we've done our algebra. We have a bunch of sums, and each sum only has a single power of x. So we're going to go through our shift, peel, combine. All right. Well, let's start by doing our shift. Do we need to shift? Well, the good news is, for 3 of our sums, we don't need to do very much. We like what we see. This sum, we're going to have to do something. Okay, so we say, all right, for this sum, we're going to let k minus 2 be L. or if you like, L would be, sorry, L plus 2 is K. All right. Now, before we go too far, let's talk about something. Let's talk about the start here. Now, initially, we're at 0. When we go to L, where will we be? We'll be at -2, which seems strange. But where can we start? Well, notice when you plug in 0, you get 0. When you plug in 1, you get 0. So we say, oh, well, anticipating that we're going to be dropping our start down by 2, and let's go ahead and move our start up by 2 ahead of time, just so we can save ourselves a peel step. All right, so I can start at 0, 1, or 2, so I'll start at 2. They might say, well, wait, why didn't you do that here? Well, I didn't do it there because I actually like that. Because I like the fact that it starts at 0. So I want everything to start at the same place. All right, well, we're running out of space, but that's okay because we're not running out of paper. After all, remember, it grows on trees, right? Okay, so I'm going to move this up just so we can keep going along. And, okay, there we go. So we are now going to update with our new index L. Here we go. So we have the sum. Now for 3 of these, all we're doing is swapping K for L. So I want to say it's mindless, but this is a time when you want to make sure you're very careful about copying. Copying is our biggest challenge. And now here's our one we have to think about. Okay. Because we shifted our start to 2, L now starts at 0. Nice. To infinity. Now, we have C sub K. Well, that's C L plus 2. And then we have a K is L plus 2. And then K minus 1 is L plus 1. All right, then we have minus 6. Whoops. Ha 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 ha. I forgot to write down X to the L. See? If you're not paying attention, you forget things. And once you forget things, it's hard to recover. K equals 0 to infinity. CL, L, X to the L, plus 12, sum, L equals 0 to infinity. CL, X to the L equals 0. All right. So, moving right along. What do we do? Well, now we checked we need to peel. No, because we kind of did a preemptive peel. And that's when we said, hey, by changing our starting, we can avoid peeling. So we've done our shift, our peel, so we're ready to combine. All right. Well, so we have one sum to rule them all. Now, I'm going to think of it as sort of 2 things. So there's the CLs, and so I have 3 pieces which have CL. So I'm going to put those together. All right, so we have CL, and then we have L times L minus 1 from this part. Here we have minus 6L, and then here we have plus 12. Okay, so those are our 3 terms with CL. And then we have our CL plus 2. And, well, there's only one of those, and that's right here. And so we say, okay, great. And so don't forget the minus. And we have L plus 2 times L plus 1. And then all of that times X to the L equals 0. Okay. Good. Whew. Progress. Progress is being made. We are actually doing really well. You hanging in there? All right. Good. It's all right to take a break if you need it. We're approaching a good point in the problem because we've done a lot of the hard work. Okay, so we're ready to start talking about our recurrence relationship. And that comes from saying here is our coefficient for x to the L, for L starting from 0 all the way to infinity. It has to match the coefficient over here. Well, that says all of these terms have to be 0. Not just the constant term, but the constant times x, the constant times x squared. They're all 0. So our recurrence relationship, well, we can say it's CL, and let's go ahead and start working on this. We'd have L squared minus L minus 7L, sorry, minus L minus 6L gives us minus 7L, and plus 12. And then we have minus CL plus 2, and then we have, well, L plus 2, L plus 1 is equal to 0. Now, you could justifiably say that's the recurrence. I'm going to do one more thing. I'm going to actually solve for CL plus 2. And so I'm solving for the largest subscript. So CL plus 2, what do? You move it across and divide. Well, that's your coefficient CL. And notice that L squared minus 7L plus 12 factors. What does it factor as? Well, it's L minus 3, L minus 4, right? Check. L squared minus 4L minus 3L is minus 7L plus 12. Divide that by, and downstairs L plus 1, L plus 2. All right. Okay, so we have our recurrence. Okay, this is great. This is great. Check. Doesn't it feel like we've made wonderful progress? Okay, all right. Now, what are we going to do next? Well, we're going to find the solution, and we'll find two solutions. So let's start here. All right, y of 0 equals 0, y prime of 0 equals 1. All right, so, whoops. Let's see, what can I put down here? And there we go, there we go. So y of 0 equals 0, y prime of 0 equals 1. Now, y of 0 is our C0, and y prime of 0 is our C1. So let's talk about our C2. C2 would be L equals 0. So according to this, C2 is C0 times minus 3 minus 4 over 1 times 2, but C0 is 0. So this is 0. All right, what about C3? Well, that's C1. And so now we're thinking L equals 1. So 1 minus 3 is minus 2. 1 minus 4 is minus 3. Downstairs, we're going to get 2 times 3. Well, the 2's cancel, the 3's cancel, the minuses combine, so what we end up with is C1, and that's 1. Cool. All right. Progress. Okay, well, let's do more. C4. Well, that'll be C2 times. Now, notice, once I know it's C2 times something, it's always going to be 0. But okay, we'll go ahead and write it down. Now, this would be L equals 2. So we're going to have 2 minus 3 is minus 1, then minus 2. Downstairs, we're going to have L equals 2. So 2 plus 1 is 3. 2 plus 2 is 4. But since C2 is 0, we get 0. In fact, what's going to happen? C6 will be 0. C8 will be 0. C10 will be 0. So the rest are 0 for the evens. what about the odds? Okay, all right, okay, hold on, we'll get there. C5, what do we see? Now C5 would be L equals 3. So what does that give us? Well, C3, then we're going to have 3 minus 3 is 0. Then 3 minus 4 is negative 1. 3 plus 1 is 4. 3 plus 2 is 5. Wait, 0. So that's 0. But wait, we just talked about, remember how we said we go 2 back? And because when we went 2 back here, we got 0. We got 0. So what is that going to say? What's C7? 0. C9? 0. The rest of the terms are all 0. So the great aha is we get that, well, C1 is 1, C3 is 1, then CK equals 0 for all other K. So this big sum K equals 0 to infinity of CK x to the K, well, we only have 2 terms. It becomes, well, C1 is 1 times x to the 1, C3 is 1 times x to the 3. So x plus x cubed. So x plus x cubed is a solution. See, we found it because we found the whole series, and it just turned out that most of the terms vanished. All right, now we're going to do the same thing, but with different initial conditions. Just because things worked out nicely for one set of initial conditions does not guarantee it'll work out nicely for the other. So what do we have to do? We have to do our whole thing, right? So we're going to follow the work done here. We're told that y of 0 is 1, y prime of 0 is 0. So that's our C0. There's our C1. Now I can just read off here. What do we have? C2, well, that's C0 times minus 3 times minus 4 over 1 times 2. Well, okay, the minuses cancel. 3 times 4 is 12, divided by 2 is 6. So that's 6 times C0, which is 6. C3, well, it's C1 times stuff, but we're going to use the same idea. Say, well, wait, we know C1 is 0, so that says this will be 0. In fact, all the odds are 0, right? C5 will be 0 because C5 goes back 2 steps, and we know C3 is 0. So then C7 will be 0 because it goes off of C5. So all the odds are 0. So we got to work on the evens. What about C4? Well, for C4, that's going to be where we have our recurrence relationship. Here we go. We'll see it there. And, well, we can also work from it up there. That's C2 times minus 1 minus 2, 3 times 4. Well, we know C2 is 6. So we have 6 times 2 is 12. Divide by 12 is 1. Now, what about C6? Well, C6, because we already talked about the odds are 0, so C6 is C4. Now, that would be L equals 4. So that's times 4 minus 3 is 1. 4 minus 4, 0. And downstairs, 5 and 6, but we see 0. And now, again, C8 will be 0. C10 will be 0. All the rest are 0. So we get the following. We have that C0 is 1, C2 is 6, C4 is 1, then CK equals 0 for all other K. All right, so what does that say? Well, that says our sum, k equals 0 to infinity, of ckx to the k. Well, we have our constant term, then we have plus 6, and that's attached c2, so that's x squared. And then we have plus 1 times c, since that's c4, x to the 4th. And that's our whole solution. So we have these two wonderful, beautiful solutions. All right, so let's recap here. So what we now done, all right, let's line up our page. We now have that our two solutions found using our series, and but they are y equals x plus x cubed, and y equals our 1 plus 6x squared plus x to the 4th. All right, so we'll pull this aside, and so we've finished what it asked us to do at the outset. We found our solutions. We found everything, though, because this is linear. So all solutions are combinations of these two. So even though this looks like a very this is going to be an unpleasant kind of differential equation, we're like, oh, this was a very pleasant differential equation. Now, when will these solutions work? The answer is these are true for all x. There's no problem here. However, we talked about the fact. Well, here's the thing. Let's solve for this in terms of like singular points, right? So y double prime minus 6x over x squared minus 1 y prime, and then plus 12 over x squared minus 1 y equals 0. What's an issue? We have singular points. So there's singular points at x equals plus minus 1. So normally, if we saw this differential equation and we were doing series about 0, because the zeros tell us that we're doing our series around 0. So normally we would say the radius would be 1. Now here's the thing. When we talked about the fact there was a subtlety that we didn't say out loud, but let's say it now. The radius of convergence given by the fact says worst case scenario. You're guaranteed it works at least this far. However, sometimes it can go past it. So our fact is just worst case. So we're guaranteed at least that far. But in some cases, such as right here, we can go even farther. So there we go. What a problem. What a problem. Okay, well, now that we've had our warm-up, let's do a few more. So let's look at this example. Consider the initial value problem. We have x squared plus 1y double prime plus 2x y prime minus 2y equals 0. Y of 0 is 1. Y prime of 0 is 0. And we're asked to give the series solution up through the first 6 terms, up through the coefficient of x to the 5th. Now, we're not going to do as much work as we just did on the previous problem, because that was a lot of work we just did. Whew. So we want to just say, okay, let's tone it down and say, okay, what do we need? Well, what don't we need? We're not asked to find the solution, and odds are pretty good we wouldn't succeed. The last problem, beautiful problem, kind of a fluke. The stars aligned, so to speak. Usually they will not align. So, all right, so we have to work this through. So we're not going to try to find the solution. We weren't asked to find the recurrence, so we're not going to. We were asked to find up through the first 6 terms. So that says, look, we're trying to find our C0, C1, C2, C3, C4, and C5. So we're going to split this into two camps. We say, all right, camp 1 is the first two terms, and here we're going to use our initial conditions. Camp 2, which is the remaining terms, C2, C3, C4, C5, this is going to come from the differential equation, and in particular, we're going to look at the coefficients. Now, which coefficients are we going to look at? Well, you start 1, x, x squared, x cubed. So that's what we're after. So we say, okay, we only need enough, only enough to get us up to those. Okay, so with that in mind, we begin. Okay, so what do we have? Well, we'll make some notes here. Of course, y is, that's the sum. K equals 0 to infinity, ck x to the k. So that's c0, c1x, and so forth, so on. Y prime, that's the sum, k equals 0 to infinity, k, ck x to the k minus 1. Well, that begins as c1 plus r2, c2x, so forth. And y double prime is our sum, k equals 0 to infinity, k, k minus 1, ck x to the k minus 2. And that begins as our 2c2 plus, we're going to have 6c3x, and so forth. All right, so let's write our terms down. We have x squared plus 1, and now we're going to multiply it by y double prime, which starts as 2c2 plus 6c3x plus, now because we're multiplying by 1, we need to keep going up to the x cubed. And so you have to figure out the pattern, right? It's number, right? So here it's 3 times 2. So the next one will be 4 times 3. So that's 12c4. And then it'll be 5 times 4, 20c5. And dot, dot, dot. Dot, 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 shorthand for the other stuff, which we won't need, plus 2x. Now, remember, there's already an x here, so how far do we need to go? Well, we're going to be multiplying by x, so we're going to need our start c1 plus 2c2x. The next term would be 3c3x squared, and dot, dot, dot. Now, why can we do dot, dot, dot here? Well, because we're multiplying the x here, so we're already up to x cubed. Okay, minus 2, and now times our y term, c0, c1x, c2x squared, c3x cubed, plus dot, 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 equals 0, 0. All right. Now, okay, we're going to very carefully start gathering. So, when we look at this, what's our constant terms? Well, we're going to have a constant term here. So that's 2c2. There won't be any constant term here. There will be a constant term here, minus 2c0, and that's our only constant term. All right, well, let's go to our next, which is our x. Well, the x squared, okay, that's not going to get us to an x, but here, 1 times 6c3, that'll do it. So 6c3, 2x times c1, So plus 2C1. And then we have our minus 2C1 times x. Okay, good, good. All right, well, now let's go to our x squared. Okay, well, what's going to happen here? Well, we're going to get the following. We'll have for x squared, well, now we can do an x squared times a constant, so that is a 2c2. We can also do a 1 times the x squared, so that's going to get a plus 12c4. Here we can do x times x, so that'll be plus 4c2. And then here we can do a minus 2 times c2, so that's minus 2c2, and that's x squared. All right, one more to go. Okay, so our last round, we're looking for x cubes. Well, we can do x squared times the x. So that would get us 6c3. We can also do 1 times x cubed, which would get us 20c5. We can do x times x squared. So we have 2 times 3, that makes 6c3. And then we have minus 2 times c3. And x cubed. And, well, everything else. Plus dot, dot, dot equals 0. Now, we don't need to worry about the dot, 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 because we said we only need to look through x cubed. Okay, all right, how you doing? So remember, what's our mantra here? If we're not after a recurrence relationship, and we only need a few terms, we just are getting enough to make sure we get the information we need. And so we already know 2 of them for free, so we need 4 more. That's why we're looking up through the first 4 pieces, up through x cubed. And so we only wrote down enough to make sure we get the information for x cubed. So here we go. Let's start with the ones we know. C0. Well, that's initial condition 1. That's your y of 0. That's 1. C1. That's your y prime of 0, which is 0. Okay. Now we move on and we say, all right, well, for the next one, 2c2 minus 2c0, but we know c0, so minus 2 equals 0. So that tells us c2 is 1. All right, great. Now, for our next one. Okay. What do we have? Well, notice the C1s cancel. So we get 6C3 has to equal 0. Well, okay, so C3 equals 0. Great. And, all right, how about that next one? Well, the 2 C2s cancel there. So we're left with 12C4 plus 4C2. Well, what's C2? It's 1. So plus 4 equals 0. Okay, subtract 4, divide by 12. C4 minus a third. All right, good, good. Okay, and now our next one. Well, what do we see? We get 20C5, and then we get 6C3 minus 2C3, but because the C3s are all 0, those are going to go away. So that just becomes 20C5. Again, that equals 0. And so, lo and behold, C5 is 0. And now we found all our coefficients. Now, notice it didn't ask us to, find the C's. It says give the series solution up through the first 6 terms. So, what that means is we want to write down what the series starts as. Okay, so we're going to start as our C0, which is 1. C1 is 0, so we won't write it. C2, that's going to be a 1, so plus x squared. Then C3 is 0, so we won't write that. C4, minus 1/3 x to the 4th. Then C5 is 0, and so our solution has that form. 1 plus x squared minus 1/3 x to the 4th, and so forth and so on. And there we go. All right. Now you won't get any canceling crazy thing like we did before, so it would really be a big, long, infinite series. But that's all we need. And okay, I feel like this is a good place for us to stop. But keep practicing, right? The 2 main things you should be practicing when it comes to series. Get your recurrence relationship by putting your sums together. So you put your sums in, get your powers of x's, 1 power of x in each sum, shift, peel, combine, right? Shift, peel, combine. And put everything into one sum. There might be a little bit of noise at the start. That's okay. That's fine. The part inside is that recurrence relationship, and then using your coefficients, you can solve. Or you can do something like what we did here, which is say, look, you don't need to find the recurrence. You just need enough to know how it starts, maybe the first 4 or 5 terms. Then you say, all right, I can get some freebies from my initial conditions. I just need to get enough information to find the rest. And the moral is, every new coefficient in your full expression gives you an additional piece of information. So you say, okay, I just enough, right? Just enough. And there you go. Now when it comes to radius of convergence, a good rule of thumb is just use the nearest singular point. Usually we don't talk about that much beyond anything saying other than nearest singular point, so don't make things complicated. Don't complicate things. Math is not about making things complicated. It's about making things simple. And it's practice. Make it your life simple. All right. What a journey. Probably we should take some review, and we'll do that in the near future. But for now, we'll see you later. Bye.